Hi, welcome to our next level 3 integration video. In the next couple of videos, we're going to focus on a technique called numerical integration. In the last couple of videos, we looked at a really cool trick to find the area underneath a function between the x-axis and a graph. But what if we don't know the formula, or the formula is a very complicated formula? Well, we're going to look at a technique that still can estimate and give you a really good estimate of the area underneath a function, even if we don't know the actual rule. To do that, what we're going to do is break everything up into little trapeziums. For now, this is the first rule, the trapezium rule. And we're going to slowly work out the area of each trapezium section by section. You can see that so far we've got 3 sections, 3 different trapeziums. So as we progress through, you'll see that these are just little trapezium sections. Sometimes the trapezium gives a really good approximation. Sometimes it's not that fantastic because the trapezium obviously draws a straight line between the endpoints. So you'll see in some regions it's not the best approximation, but in other regions it's really good. In saying that, the ones that are above the line and the ones that are below the line tend to cancel each other out. It still gives us a very good approximation of the area. Right, we're going to introduce the width of each trapezium, and we're going to call that the height. I know you don't think of it as the height because you think of the trapezium standing up. That's probably the width, but if I flipped it around on its side, we tend to think of it as the height of the trapezium. Okay, so the first rule is called the trapezium rule, and here is the trapezium rule. Now, h is equal to the height of the trapezium, or the width of each trapezium. We're going to divide h by 2, and we're going to multiply it by all the stuff inside brackets. Now, here is what's going on. y0 is your first y value, the height at that point. y1 is your second y value, the height at that point, and we're going to times it by 2. We're going to times y2 by 2, y3 by 2, y4 and 5 and 6 by 2. Everything's going to be times by 2, apart from y0, which is your initial, and yn, which is your last y value. So just keep that in mind. We keep y0 the same and yn, the last value, the same, but everything else gets doubled. All right, let's show you how to do it with an example. Approximate the area of the function y equal to 0.2 times e to the power of 0.75x. Now, I know we have the formula right now, but in a lot of applications we don't, and we estimate the height. We're going to use the trapezium rule, and we're going to use values of x between 0 and 3, using trapeziums with a height of 1. Right, so here is the graph, and here are the 3 trapeziums we've got set up between 0 and 3. Each trapezium has a height of 1, a width of 1. Right, you'll see it's a little bit inaccurate, but we'll find out how good our approximation is shortly. So here's a table. Let's go through each of the x values and put them into the rule to work out y values. So that's y value when x is 0. That's the y value when x is 1. That's the y value when x is 2. And that's the y value when x is 3. Right, now let's use the area rule with the trapezium. So we're going to go 1/2. H is 1 because a height of 1. Times our first y value we're not going to do anything with, our second y value we're going to double, our third y value we're going to double, and our last y value we're going to leave it alone. So when I calculate that, that gives me an area of about 2.37 square units, which when we go back and compare to the actual true value by doing actual integration, it's a pretty good approximation. Now, if I was to redo that whole thing again and split it up with heights of 0.5 instead of 0.1 and have more x values, you'll see that I will get a much better accurate 2.29 square units, which is much more accurate to the true area. All right, thanks for watching.